As I've been working on my 386DX build and the 386SX upgrade for my 286 build, I've had to figure out how to get better at timing and understanding timing of different things in the system. There's a lot of different control signals, and those control signals are spread over a few different generators of those signals, whether it's a PSOC. I have 2 PSOCs on my 386DX as an example. I have a couple of PAL chips. And then, of course, there's the processor itself, whether it's a 386SX or the DX, are generating additional signals too. And if I get into the hardware reference manuals for the SX or the DX, there's all kinds of information on what timing should be. And as I'm trying to put all this together, put these different pieces together and understand from the documentation what I should be doing, I need some way to actually view that. And I decided to just give it a shot using an STM32 if I could use that as, really an inexpensive way to do some type of analysis of those signals on my board. And so this is the board that I'm using. It's a Nucleo H723ZG. Now, previously I was using an Arduino, and that Arduino works fine. Just doesn't have enough inputs to capture all the stuff I want to use. So on my 286, the Arduino was great. But once I get to the 386DX, I have twice as many data lines, twice as many address lines, and it seems like more control signals that I have to be paying attention to. So I thought I would go with this Nucleo. The upside of it is that it has a lot of input pins, so there are plenty of opportunities for me to bring in signals. The downside is it's really a 3 volt setup, and some of the pins are 5 volt tolerant, but not all of them. And so I have to be careful about when I run what levels into which pins. And so I built kind of a carrier board for this that is an ISA card form factor. And it looks like this, so that I can, off to the left, just drop in that Nucleo board. And then I have choices. I can either pull in signals from the ISA bus, or I can pull signals from these external input headers up top, or a combination of the two. And so I started to build this out, and it looks something like this. And probably one of the first things I'll call out, I'm not really worried about it, but these headers that I have melt pretty easily. And as I was doing some of this IC work, fixing some stuff after I had already put these headers in, I did manage to melt some of these. Not a big deal. It's not affecting anything electrically, but it just looks really bad. But I wasn't about to go pull those out just because of a little melted plastic. But what you're seeing on this board is I have these series of ICs, which are just voltage level shifters. And I have the ISA slot down here, and I have these external inputs up here. And every input pin coming into these voltage levelers is coming from a middle row of one of these headers over here. And what I can do, for example, if I take these first 3 right here, this top pin is coming up from up here, and the bottom pin is coming from down here. And I can choose. So I want to pull a signal off the ISA bus or pull some other signal off an input header. And I just set a jumper on one or the other. And here's an example down here where I had 2 jumpers saying pull these 2 signals from the external bus, not whatever they're mapped to on the ISA bus. But this gives me flexibility. So it's a whole bunch of pin headers and a whole bunch of jumpers, but that's not a big deal. But what that allows me to do then is, maybe pull all the basic address 0 through 23 off the ISA bus, pull the data 0 through 15, some of the ISA bus signals, and route those over through these into different inputs, basically on my STM32 card, basically different ports there. And when there's something not on the ISA bus that I need to get to, I'll just plug it in somewhere up here and set the jumpers to pull from up there. As I did this, I also did put in some SIPs on all of the incoming signals so I could pull those up or down. I've done some testing and it actually runs better without anything there, so I've just gone without those. You'll see on the version later that's actually populated. I do have all of these in. I have tried testing with and without pull up, pull down, and different resistance levels, but I've just not found that it actually seems to cause more problems. So maybe it's something in my setup, but I pulled those actual SIPs out. I have the socket so I can experiment further later if I want. So then putting the card in, it looks like this. And, you know, the nice thing about this is I'm getting the majority of my signals just from the ISA bus. I can just pop this into an ISA slot. I'm not pulling power from the ISA slot. I'm intentionally just pulling separate power over here so that I can power this with whichever power source makes sense. And I am powering this card separately too. I'm actually feeding it from an external power supply instead of pulling from the USB power. And maybe later I could tap into this PCB underneath it very easily, but I'm running that to a separate power supply for now. Now, as I was building this out, I did have to do some debugging of my debug card. And so that's what this kind of looks like on the left. I've got this little debugger that I built. Really simple. It's just a bunch of dip switches. And I can turn on and turn off basically output. And then I can also have another 16 bits of input that I can plug in here. So I can send out a signal. I can read in a signal simultaneously and just kind of check, what am I sending? What am I receiving? Or maybe this is on the inside of a transceiver, this is on the outside, or a latch or something like that. But here you can see that I'm just simply connecting these outputs into those middle rows over here and toggling values and then trying to read that from the computer, for example, through the USB on this up here, which is, here's this USB cable, just to see if what I'm setting is actually what I'm reading on the card. And what I found was that it wasn't as simple as I was hoping or expected it to be. I would run signals into one of the ports. I think it's ports A through F that I'm using, but there's also a port G. But each of those ports has 16 pins, and that's on this card getting into this processor. But I found a lot of those ports and those pins are already used for other things on this card. You can't just use them even though there's connections for all these ports. Or signal pins, I/O pins, GPIO, maybe to be more generic here. So what you have to do then is you have to flip this card over, and there's all these solder bridges, and I had to modify at least 20 different solder bridges. I had to open up some of the solder bridges that were already closed, and then I also had to close some of the solder bridges that were previously open. I had to remove a couple of resistors, and I think I had to change one jumper. But that was a bunch of just reading through the documentation for this specific board and understanding if I wanted to use a certain GPIO pin that was already previously set for some other function out of the box, I would have to open up that solder bridge to make that work. And so through all of that, then I was just doing testing to make sure I could set 16 values on a port, read it on the PC correctly through the USB. And then if I got that port working, I moved on to the next port and referred to the documentation and updated the settings on this card physically as I was going. So eventually got all that working so that this was able to come in, set my values, send them into these pins, which would go to the voltage level shifters, which then went into this card, which then USB goes to the PC. Maybe one other note on this card here, I am using USB here, and it's a 12 megabit USB that I'm using. I found out that this card natively does not support high-speed USB. It only supports full-speed USB. Now the chip supports it, but the card, this overall card doesn't. You have to go get an external transceiver that I would have to put into my card here, my circuit. So if I do happen to spin another version of this background PCB, there's probably a couple of changes I would make to it. I would add an additional couple of voltage level shifters so that I could hook up one more port, this port G, I think it was on the card. Basically, I've got, let's see, port A, B, C, D, E, F that these all go to, and I think there's a G maybe there was even an H. I'd have to go double check. But add a couple more voltage level shifters so that I could take in more inputs. And the reason I say that is some of the pins I wanted to use in these ports I couldn't use. For example, the serial interface was using some of the pins I thought I'd be able to use. So having another full port of 16 I/O pins to work with would be handy. And then I would add this ULPI transceiver, and that would also take up some of those pins, but get that added on here physically. So I would have basically a connection from this PCB to my ISA card, which would then have the USB connector that would go to the PC, and I'd be able to run at 480 megabits instead of 12 megabits. Minor upgrade, and I can probably still do that now. I just have to order up one of these transceivers and get it wired in here. So that's the general setup that I'm using for this, and it seems to be working pretty well. So then what I'm doing beyond that is I've plugged this into, for now, my 386DX that I'm playing around with. And it is an ISA card, so I can just plug it into an ISA slot. But I have this little extension, ribbon cable extension, so I can just flop this over and lay it down and do probing with my oscilloscope and things like that. And that works out really well, so that it can just be laying here. But later, I'll pull this out. I won't need it. And then what you're seeing here is I've got a little power adapter coming in where I'm powering this board here. I'm powering the host board, the ISA card, through the main 386 power supply over here. Now, one nice thing is because I put all these headers up here on what's now the right side or the top of the card, these externals, if I have a case where I need to pull signals and I'm not using an ISA bus at all, this just won't plug into an ISA slot. It'll just be a standalone card that lets me take in, all of these input signals. But in this case, I'm pulling a bunch from ISA, and then I'm pulling a bunch from all over the board. And for example, I had to pull the top, this would be address lines. So address lines 24 to 31, I had to pull from the 386 system because those are not available on the ISA board. So I pulled those, and then the jumpers would be set to reflect that these pins are coming from the external instead of from the ISA bus. And then for data, same thing. I had to pull over the top 16 data lines from the data bus on the 386 because those aren't available on the ISA. And then I have tons of just messy different control signals, either from the processor or from the PSOC or other control chips that are trying to set up timing and do everything on my board here. And then with that, I wrote a little Windows interface that lets me take what this is reading for data and show me. For example, this is just it during a boot up. I have it look for, and when it sees the starting of my ROM read at FFF0, it'll just highlight it in blue so it catches my eye quickly when it goes by. But then from there, I can see that it's reading a value of 0E or 00EA, a bunch of zeros, and then when it gets to the next address, F4, it should be reading something. Then it gets to F8, and I can see what is it reading when it gets to F8 for values. And I know something's not right here, and I'll explain that here in just a minute. I'm doing some different experimenting here. But what it should eventually do is it should read the F0, F4, F8, FC, and I should see it jump over to my C0000, which is the start of my ROM actual code. And in this setup, I'm not getting to that point just because I've broken some other stuff as I've been tinkering around with this. And again, I'll say more about that here coming up. But with this, then I can also show different signals up here, and I can choose which signals I want it to show and kind of plot as it goes off to the right. So here I'm reading maybe a line, but for that one line, there may have been a whole bunch of activity up here. And I'm recording that and showing that up top. So I can see in this example a clock and my, clock 2, clock, reset, MIO, DC, WR, ADS, and ready. Those are the ones for now that I'm showing up here. But there's a whole bunch more I'm going to add to this as I go. So this is what my actual mess of a setup looks like right now. And over to the right again, here's this little card that I put together, and on top of that is this Nucleo board with the STM32. It's connecting into my ISA slot through this little ISA extension that I've got. I'm pulling data from up here on this little daughter board that I built, or this little breakout board that goes from my 386 over to this other board that's just hosting 4 ROM chips. And that underlying green board is just stuff that I wanted to use to affix some stands. So that underlying green board is not doing anything electronically or electrically. But I had to pull off my debug headers onto the 386DX board over to this other little board, and from there I duplicate the signals out, or I have little pin headers I can connect to and run it both to the ROMs, and I run some of these signals over to my debug card. And that includes those extra address lines, and then of course the high 16-bit data lines, that high word I need to get over. And then you can see I've got all kinds of other signals that I'm just pulling either off of my PSOC, or here's a little spot that I have left of the processor, which is a bunch of the normal control signals being used in the system. And so I'm pulling a bunch of those, and all of these are then going over into that card where I'm choosing either to pull from the ISA slot or these external signals coming in. That little card I have off to the left is just doing clock. The nice thing I like about that is I've got switches. And so on that card, I can start the clock, stop the clock. I can pause it. I can speed it up, slow it down. It just gives me a lot of control over the clock. I think at some point I will actually have the STM32 generate the clock so that when I hit something I'm looking for in the running of the system, it can actually stop itself, pause the clock itself, and give me kind of a single step or speed up, slow down type of control from the user interface for my little debugger. But for now, I'm using that card on the left because it's easy. And here's the software that I'm using. So I do a connection here to get to that STM32 card. I start it up, and then I've actually got to go turn on power to the system. So this is showing while the system has no power to it. And so I'll go ahead and turn on the power, and you'll get to see that activity here start. But this is going through the normal processor cycle startup. Now, right away, I'm going to pause it and just point out that this helps me quickly understand, is my reset, clock 2, are those 3 lines synchronized like they're supposed to be? And so from the documentation, they provide this, and it just shows that there's certain expectation of how these signals are going to come out for clock 2 in relation to reset. And so then I can look up above and see, okay, there's my reset line. So when I turned on the system, it automatically holds the reset for a time period. I have a little chip that does that. But then when that reset line drops, at that drop is where I should have clock 2 high, I should have clock high, and then I can compare to what I actually see above, and it looks like that matches what I'd expect to see based on the documentation. And it didn't, so I had to then modify, and what you're seeing here is that it's not just a send the reset through. Now, as a reminder, my PSOC is doing this reset signal, and so I take in a reset active low. I'm running it through this SR latch that is clocked on the CLK signal, and then that's sending out an active high reset. And so that should give me what is shown here, that I'm basically clocking this with CLK, and all my levels should be in sync. So that's like one minor thing I've had to do, and you really got to see the signals. For me, I've got to see these signals visually to kind of make sure that what I'm getting out is what I would expect to get out based on the documentation. So then as I continue, here's another diagram from the documentation that just shows how clock and clock 2, what's the relationship between those, and starts to show me these clock periods. Here's one where I can see this T1, T2 time and how all these other signals start to play in. And these graphics, these figures are just all throughout the hardware reference guide, so I can look at those, and I just need to work through those and make sure that what I'm actually doing for my signaling is matching what should be happening. Now, some of the challenge is that I have things like this where the documentation just shows me a 16R8 PAL, but what it doesn't do is necessarily tell me what's inside of that PAL. And maybe they'll give me a little bit of a hint to tell me how ready should work, but it doesn't necessarily tell me how WS2 should work, wait state 2. And so off to the left is my current implementation, which may or may not be right. And you can see my comment there. I have low confidence that this is currently correct. So that's the type of thing I need to experiment with, go back and read the hardware reference manual from beginning to end and really pull out any of those details that have to do with timing and see if I can get this implementation figured out correctly. But I think this little debugger I have in the background will help me with that, so that I can try to get these signals to look like what the documentation is showing me that they need to look like for this to work. And here's another case where this is something I had modified in a previous video. I get into this CS0 wait state and a CS1 wait state, and then also there's a CSIO active low signal. And I'm just looking at the schematic that I find in the documentation, and it's using this 74139. So then I'm looking at the documentation for that, looking at the schematic, and then just implementing that through this lookup table or a LUT inside of my PSOC. And that's another one of these things I can experiment with. And you can see below how I actually have that set. Just details, though, that I need to, again, continue to experiment with and make sure I'm getting the timings that I would expect. And what I have down below does not exactly match what I see in the schematic, and that is on purpose at the moment. So all of that hopefully will help me. I know that's still not the ideal type of debugging environment. This is kind of maybe I'll call it a poor person's debugger here. I'm taking a relatively inexpensive STM32, and then I'm bringing all this in and really doing the lifting through a little Windows application. That'll give me some flexibility, but it's not perfect, and I know I've got some tweaking and optimization to do with that. So I did pick up one of these. This is a logic analyzer from Agilent. It's a 1680A, and this is an old device, but it supports 136 channels at 400 megahertz with a meg of memory for some of the capturing that I'm doing. And I think this is going to give me some much improved way at looking at some of these signals. Now, the first thing I did when I got this is I kind of tore it apart and replaced the CMOS battery in it. And then it also has an old rotational hard drive that it's using that runs Windows 2000 and all this software. And I've been doing some digging on the internet, and it doesn't seem like it's easy to get fresh images of this or to even find the software to install. So I wanted to make sure I had a good backup of this. So I did pull the drive, and then I imaged it over to an SSD, and then I put the SSD back in here. And I'll keep the rotational kind of as a backup in case I somehow manage to mess up this operating system or cause problems with it. Plus, I did a separate backup of it to a USB thumb drive. But I got that SSD back in, it boots up, it seems to be running everything as far as Windows and getting into this software correctly. Now I need to learn how to actually use the software, this Agilent Logic Analyzer software. So that's on my list at this point. I will connect some of these ribbon cables that you see here. I think those actually connect right into the headers I've got on my 386 board or other boards here. Or I've got some nice little breakout boards that will help me, I think, get these cables connected to the right signals. And then I'll start learning how to capture, how do I capture similar data but better than what I have on this little debug viewer in the background. So that's what I need to spend the next, weeks, if not months, learning how to do. But that's on my list, so I'm going to start learning how to work through that. And then shortly I should hopefully I have some 386SXL processors coming in, and once I get those in, I can jump back to my 286 build, and I'm going to get the 386SL upgrade board populated with, or the 386SX upgrade board populated with one of those 386SXLs, probably connect some of this debugging equipment and then figure out how far or how close I am to getting that upgrade chip to work. So I'm looking forward to being able to do that so that I can start doing more coding on the 286 system running a 386SX. Really because I want to get into those extra registers before I get too far down the coding path. It'd be nice to take advantage of those. So that's where I'm at for the moment. I'm not sure what my next video will be. It just depends on when this 286 SXL comes in and if I can make any progress on that. And while I'm waiting, I think I'm just going to spend some time trying to learn how to use this logic analyzer from Agilent and maybe see if I can have any luck trying to clean up some of the 386DX signals based on the documentation as I read through all of that from front to back. So that's a whole lot that I've shared here, but if you have any thoughts, feedback, suggestions, as always, drop a note below, and thanks for following.